Okay, I thought it'd be worth spending a few minutes going over the Truss Analyzer and how it plays into the D3 Truss project. So this is the interface here, Truss Analyzer. It's called the Truss Analyzer. It was created by a student a few years ago, um, and what it this is just a simple program that performs the free body diagram calculations for truss geometry that you enter into it. And it's important for you to realize this is not a design machine. It's not something where you play around and create a design um, and then say, hey, I designed this cool truss. It's about using engineering principles to design trusses, and this program can help you by just doing the automated calculations to save you time so that you don't have to do hand free body diagram calculations. Okay, so let's go over the interface a little bit. First thing I want to point out is just this section over here, the tools. Grid snap, I would set this at 0.25 because that's just saying that's the smallest amount that I can move anything I'm moving. So I'd rather have it accurate. And then I've got joints, members, and loads. So how do I navigate in this interface? If I select something, let's say I want to move this joint, I select it, and then I say where I want to move it to. I click on where I want to move it to, and it moves it. Then I have to do that again if I want to move it again. If I want to do something else, I have to come down here and let's say I want to add a joint. I have to select add a joint and place the joint. I'm going to move this back. So then let's say I want to add a member now. I go to add member. I select the joints that I want to add between, and it will add the members. Now remember, this is just math. So these are mathematical, these are geometric lines and points, so they have no volume. So in order to design a real truss, we have to apply the material, or we have to say what the material is, which means using the equations that we've learned through this semester. So remember that this is not really the truss itself. This is a theory of the truss that we use to with further steps. Let's go over some more stuff in the interface. Symmetry. This truss, we want to be applying simple planar truss theory, which means our truss needs to be symmetrical. So make sure you have the symmetry button selected. What that means is that anything I do on this side, the white side of the screen, will be replicated on the gray side, thus guaranteeing that this geometry remains symmetrical. Down here we see truss condition. It says yes. If it says no, it could mean several things. You could just be making some mistakes. Like for example, if I want to add a joint, let me get rid of this. If I want to add a member, let's say so I add a joint here. That's not actually adding anything, right? I mean, I'm not. Let me move this now. Right? I have to actually, and if this was more accurately done, where it looked like it was right on the line, you might assume that or you might forget that you cannot, that doesn't, see that right there, that's still one member, right? So if I want to set a joint there, I have to delete these other members and redraw them. And you'll see now that this is not a truss, it says no truss condition. And that's because we don't have number of members equals 2 times the number of joints minus 3. That's the relationship in simple planar truss theory that guarantees us that we're going to have a, with the end conditions we have here, hinged and roller, that we're going to have a statically determinate geometry. But another way to look at it is if you think about it, if you're adding trusses, you need to add 2 members in a joint. Once you have a truss, that's some multiple of that is going to add triangles to your truss. So I'm going to go back to where I was. Okay. So now let's add a load to this. So I'm just selecting load. I'm going to add it to the top point. We have a truss condition, yes. It's actually, notice here too, we have the material length and the truss height. You need that information for other calculations. The material length is just how it's adding up the lengths of these members. So this program also uses the Pythagorean theorem to calculate the lengths of the members. You could do that yourself, but it's doing it for us, so that's awesome. If I go to forces here, um, now I have the free body diagram calculations applied. And what I'm saying here is I applied 100 pounds to the truss. This member is negative 106.3 pounds, so it's in compression. That's why it's red. This member is 93.75. It's green. It's positive. It's in tension. So this is the free body diagram calculations you guys have learned how to do. But I call this then the load ratio. We don't know what this truss will fail at. We just know that when we load when we load the truss with some amount up here, that we will output the load on this member. So that's why I would suggest always using 100, because then that's going to be easy. That then becomes a ratio. This is the load ratio, 1 to 1.06 for this member, for this geometry. Okay, so then the idea here is, let's see if there's anything else you should know about that. You have member numbers that are determined by the program and the links like I showed you in the forces. There's this section over here, buckling analysis. In my sections at least, I'm saying do not use this. What this is, you can see that it's a equation of a line. So this is, let's say we had a bunch of data that we did in week 3. We could put all that data together in one collective Excel sheet, lay out the data, LU in the X, failure load or PCR in the Y, and then we could apply a linear trend line and get this equation and put it in here. And then if we did put an equation here, like let's say, I'm just gonna make something up. I don't remember anything that even makes sense, but this might be right, something that we now get a failure load for. Now this is crazy. So and there's I won't even go into why that would be crazy. I think actually maybe it's 35 would be at least give us a number that's makes sense, right? So this is saying now that the two members of compression are failing and the max load on the truss is 21.18 pounds. But where is that coming from? If you look at this is, sorry, I can't show you the whole thing because I've truncated my screen so that for this video. But you may remember these graphs from the week 3 buckling assignment, and we were trying to compare, or we were plotting Euler's critical buckling load equation and Johnson's to get the theoretical layout so that we could use this in this truss project. But also we were plotting our theory, and I'm not going to say more about that because all I'm talking about is the Truss Analyzer right now. But I did want to mention that, so this would be, for example, here's some data, the black dots, and we might then apply a linear trend line to this and put that into that equation into the Truss Analyzer. The problem with that, for example, is this is actually, it looks like this data is closer to hinge fixed, and we know from our simple planar truss theory that trusses need to have hinged connections. So what would we do with that? We need to think about that. But also, it shouldn't be linear. Neither of our theoretical calculations have linear trend lines. And so just applying a linear trend line to the data is kind of a lame way of doing it. So that's why I don't use this this equation in my sections. Your professors may say something different if you're in different sections and you're watching this, so pay attention to them. But then the idea here is that we can now export this data to Excel. And if we go to File, I haven't done this recently, so I got to remember where all this stuff is. There is, so this is just saving. Yeah, we can go to All Files, Save All Files, and that's going to save the MATLAB file so that we can reopen this file that we just made. It's going to save a JPEG of each of these. It's going to of this image, so with the labels, the links, and the forces. And it's also going to save a CSV file of the data from these 3 data streams. So it's going to have the label numbers tied to the member links, tied to the forces that basically the load ratio. And you'll get that as a CSV file, and you can bring that into Excel, and then use that as the guts data for your modeler. And then so the point is that now that this is an easy place to iterate. So now if I want to, for example, make another truss here, and go to the next step, I might say, okay, I'm going to add a joint somewhere over here. I'm going to delete these members, because I actually need to add another joint here. See, I'm not sure why these aren't deleting. That seems strange to me, but just might as well delete them. And we should. Since it's symmetrical, it should be deleting automatically, but whatever. Then if I add all my members, we're still at truss condition no down here because I need a member here to get to my correct symmetrical members. Number of members equals number of joint, 2 times number of joints minus 3. I now have a truss, and I have new load ratios, new links, and new data that I can output. Anyway, that's the basics of the Truss Analyzer. I hope this helped.